Hey everyone, get ready for some mind-blowing space news. The James Webb Space Telescope, our incredible eye on the universe, has just spotted something that's shaking up what we know about galaxies. It's found supermassive black holes that were previously completely hidden from us. These aren't just any black holes. They are behemoths that existed in the very early universe, much earlier than our theories predicted they could grow so large. So, what does this mean? It challenges our entire understanding of how galaxies are born and evolve. We thought we had a pretty good picture, but these new discoveries suggest there's a huge piece of the puzzle we've been missing. It seems these cosmic giants might play an even bigger and earlier role in shaping the universe than we ever imagined. Isn't that amazing? We're literally watching the story of the cosmos get rewritten. Stay tuned for more updates, and don't forget to subscribe. Hey everyone, and welcome back to the channel. Today, we're diving into one of the most mind-bending discoveries to come from the James Webb Space Telescope, or JWST. It is a story that reaches back to the very dawn of time and challenges everything we thought we knew about the cosmic giants lurking at the heart of galaxies, supermassive black holes. For decades, we have had this neat and tidy picture of how galaxies and their central black holes grow up together. The idea was simple. As a galaxy pulls in more gas and stars, it grows bigger. The black hole at its center gets a share of that cosmic buffet, and it grows bigger too. They evolve in a beautiful, synchronized dance, maintaining a predictable ratio between the black hole's mass and the galaxy's mass. This was the cornerstone of our understanding of galaxy evolution. It made sense, it was elegant, and all our observations seemed to support it. Until now. JWST, with its incredible infrared vision, has peered deeper into the cosmic past than ever before, looking at galaxies as they were when the universe was just a baby, less than 1 billion years old. And what it found has thrown a massive wrench in the works. In these ancient, infant galaxies, Webb has spotted supermassive black holes that are, frankly, way too big for their britches. Imagine looking at a photograph of a 1-year-old child who happens to have the body of a full-grown adult. That's the cosmic equivalent of what astronomers are seeing. These early black holes are 10 to 100 times more massive than the established theories predict they should be, given the size of their host galaxies. They're not just a little overweight, they're cosmic behemoths in toddler-sized galaxies. This completely upends that neat, synchronized growth model we held so dear. It's like the black holes got a massive head start, growing at a pace that seems almost impossible. So, how did this happen? How did these black holes get so huge, so fast? This is the billion-dollar question that has astronomers scratching their heads and racing back to the drawing board. The old model of slow and steady growth just doesn't cut it anymore. We need a new story, a new mechanism. One of the leading new ideas is the concept of direct collapse. The traditional theory suggested that black holes start from the collapse of a single massive star, and then slowly grow by gobbling up gas and merging with other small black holes. But that's a slow process. The direct collapse model proposes something far more dramatic. Imagine a colossal, primordial cloud of gas and dust in the early universe, so immense that instead of fragmenting into countless stars, the whole thing collapses in on itself all at once. It bypasses the stellar phase entirely and forms a massive black hole seed right from the get-go. These seeds could be tens of thousands or even hundreds of thousands of times the mass of our Sun. Starting with such a hefty seed would give these black holes the head start they needed to become the giants Webb is seeing in the cosmic dawn. Another fascinating possibility involves the nature of the early universe itself. Back then, the cosmos was a much denser place. Galaxies were packed closer together, and streams of cold, dense gas flowed between them like cosmic superhighways. Perhaps these early black holes weren't just sipping gas from their own galaxy. They were feasting directly from these massive intergalactic streams. This would be like hooking up a fire hose of cosmic fuel directly to the black hole's accretion disk, allowing it to bulk up at an astonishing rate, far faster than its host galaxy could grow. This scenario paints a picture of black holes as independent predators, not just passive partners in galactic evolution. These discoveries are forcing us to rethink the very role of black holes in the universe. We used to see them as a consequence of galaxy formation. The galaxy forms first, and the black hole follows. But what if it's the other way around? What if these gargantuan, Overmassive black holes are actually the seeds of galaxy formation. Maybe their immense gravity is the primary anchor that pulls in gas and dark matter, kick-starting the formation of the galaxy around them. Their powerful outflows and jets of energy could then regulate the galaxy's growth, shaping its structure and determining how many stars it can form. In this new picture, the supermassive black hole isn't just a resident of the galactic core, it's the architect. The implications are profound. If black holes are the architects, it changes our entire narrative of cosmic history. It means that to understand how we got from the Big Bang to the beautiful spiral galaxy we live in today, we first need to understand the origin story of its central monster. And Webb's work is far from over. Each new image, each new data set, brings us more puzzle pieces. Astronomers are now using Webb's spectrographs to analyze the light from the regions around these ancient black holes. By breaking down the light, they can figure out the speed and composition of the gas flowing into them. This will help us test the different growth theories. Are we seeing evidence of a direct collapse event? Or can we trace the fire hose of cold gas streams feeding these beasts? The answers are hidden in the light from 13 billion years ago, and JWST is the time machine that's letting us read them. This is what makes science so exciting. It's not about having all the answers. It's about finding a discovery so profound that it makes you question everything you thought you knew. It forces you to be more creative, to imagine new possibilities, and to push the boundaries of knowledge. The discovery of these overweight black holes isn't the end of a story. It's the explosive beginning of a whole new chapter in our quest to understand the cosmos. We are living in a golden age of astronomy, and thanks to the James Webb Space Telescope, the universe is proving to be even weirder, more wonderful, and more mysterious than we ever imagined. What do you think is going on in the early universe? Are these black holes the seeds of galaxies? Or is there another, even wilder explanation we haven't thought of yet? It's like finding a fully grown redwood tree where you only expected to see a tiny sprout. This completely messes with our established timelines for how galaxies and their central black holes grow up together. Today, we're diving deeper into the chaos. What exactly does this mean for our understanding of the cosmos? Are our favorite theories about galaxy evolution completely wrong? Let's get into it. The standard picture, the one we've been working with for decades, is a story of co-evolution. A baby galaxy forms, and at its heart, a small, seed black hole appears. This seed could come from the collapse of a massive first-generation star. Over billions of years, this seed black hole gradually feeds on the gas and dust swirling around it. It also merges with other black holes when its host galaxy collides with another. It's a slow, steady process. The galaxy grows, the black hole grows. They're like dance partners, each influencing the other's moves in a cosmic ballet that spans eons. We see this relationship everywhere in the modern universe. There's a well-established correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. It's a beautiful, elegant theory. And JWST might just be tearing it to shreds. The black holes JWST is spotting are not just a little overweight. They are monstrous. We're talking about black holes that contain a significant fraction, sometimes even up to 10%, of the total mass of their entire host galaxy. In our own Milky Way, the supermassive black hole Sagittarius A is a mere fraction of a percent of the galaxy's total mass. So these early universe discoveries are completely out of whack with what we see today. They're overmassive, as astronomers are calling them. This isn't just a minor anomaly, it's a fundamental contradiction. If the galaxy and black hole are supposed to grow together, how did these black holes get so huge, so fast, while their host galaxies were still just tiny toddlers? This leaves us with two mind-bending possibilities. Possibility 1. Black holes grow way faster than we ever imagined. The standard model of accretion, where gas trickles down onto the black hole, might not be the whole story. Perhaps in the dense, chaotic environment of the early universe, there were mechanisms for super-efficient, rapid feeding. Some scientists are proposing ideas like hyper-Eddington accretion, where black holes gorge themselves on gas at a rate that was previously thought to be physically impossible. Imagine a fire hose of cosmic gas being funneled directly into the black hole, bypassing the usual traffic jams of an accretion disk. This would allow them to bulk up incredibly quickly, far outpacing the growth of their host galaxy. But then there's possibility 2, which is even more radical. What if the black holes came first? Instead of a galaxy forming and then seeding a black hole, what if a massive black hole formed first and then acted as the gravitational seed around which the galaxy itself began to form? This is the black hole first, or primordial black hole model. In this scenario, you don't start with a small seed from a collapsed star. You start with a heavy seed, a massive black hole, that formed directly from the collapse of a gigantic cloud of primordial gas in the very early universe. We're talking about black holes born with a starting mass tens of thousands or even hundreds of thousands of times that of our Sun. This concept completely flips the script. The black hole isn't a consequence of the galaxy. The galaxy is a consequence of the black hole. This massive central object would act as a gravitational anchor, pulling in gas, dust, and dark matter, effectively building its own galaxy from scratch. This would elegantly explain why we're seeing such massive black holes in relatively small young galaxies. The galaxy just hasn't had enough time to catch up to the pre-existing behemoth at its center. This is a huge paradigm shift. It changes our entire perspective on where we came from. We thought galaxies were the fundamental building blocks, but maybe it's been about the black holes all along. So, how do we figure out which of these wild ideas, if any, is correct? This is where the power of JWST truly shines. It's not just finding these objects, it's allowing us to study them in unprecedented detail. By analyzing the light from the host galaxies, astronomers can measure how fast stars are forming. If the black holes are growing through hyperaccretion, we might expect this process to have a dramatic effect on the surrounding galaxy, either by blowing gas away and shutting down star formation, or by compressing gas and triggering bursts of it. JWST can also look for evidence of heavy seeds. If these primordial black holes were common, we might be able to spot them directly or see their gravitational influence on the surrounding matter even before a large galaxy has formed around them. Scientists are now designing specific observation programs for JWST to hunt for these very signatures. They're looking for incredibly red, distant objects that might be the quasars powered by these direct collapse black holes, or searching for the gravitational lensing effects that these isolated massive objects would produce. Every new image, every new spectrum from JWST is a clue in this cosmic detective story. What's so exciting is that we're living through this scientific revolution in real time. These aren't just abstract theories, they are testable hypotheses. The data is flowing in, and the models are being frantically updated. It's a messy, chaotic, and thrilling time to be an astronomer. The universe is showing us that it's far more strange and creative than we ever gave it credit for. Our neat and tidy story of coevolution might be a special case, a description of how things work now, but not how they began. The early universe was a different place, with different rules, and the James Webb Space Telescope is our time machine, allowing us to witness that epoch for the first time. The discovery of these overmassive black holes isn't the end of a theory. It's the beginning of a whole new chapter in our quest to understand our cosmic origins. It forces us to ask bigger, bolder questions. Were black holes the architects of the cosmos? Did the giants that lurk in the center of every galaxy, including our own, come first, sculpting the starry homes we see today? But for the first time, we have the tools to find them. Thanks so much for joining me on this deep dive into the cosmic unknown. It's a wild ride, and we're just getting started. If you enjoyed this, make sure to like, subscribe, and hit that notification bell so you don't miss our next exploration. What do you think came first, the galaxy or the black hole? Let me know your thoughts in the comments below. See you next time.